So our last video in this section is just going to be getting some practice applying all of these geometries that we've talked about. And a common way that this is posed as a question, maybe on a homework or an exam, is you're given a formula for a molecule, say this molecule, sulfur tetrafluoride here, and you are asked what is the molecular geometry of this compound. And so there's a few steps involved here, right? So first you want to draw the Lewis structure. And sometimes you may be given the Lewis structure, but often you need to draw it yourself. And then from the Lewis structure, we can determine for the central atom how many bonds and lone pairs are around that central atom. And once we have that, we can figure out what the geometry is. So let's go ahead and draw the Lewis structure here first. So we'll go through our process that we always do. So there's 6 valence electrons for sulfur, plus 7 for each fluorine, so 4 times 7, which gives us a total of 34 electrons. So 28 plus 6 is 34. So then we're going to draw our sulfur in the middle, since it's listed as the first atom and is the least electronegative. So it's going to be the central atom here, and all our fluorines are on the outside. And then we add all the lone pairs to all the fluorines to complete the octets on the outside atoms, and then we count. All right, so we're going to have 8 electrons around each fluorine. There are 4 of them, so this structure has 32 electrons, so we still need 2 more. And so our 2 more are going to go on our sulfur. So I'll draw them as dots there. Okay, so that is our Lewis structure. Right, and we could have done that with everything. This is just a rehash of what we've done in the previous chapter. So then the question is, what's our steric number for this molecule? All right, so we have 4 bonding pairs and 1 lone pair, or non-bonding pair. And again, we're just thinking about the sulfur, so we don't need to worry about the lone pairs on the fluorines. We're just thinking about the sulfur here. So our steric number is equal to 5. We just add those two together, and it's the steric number 5 with 1 lone pair. All right, so that means our electron pair geometry is going to be trigonal bipyramidal, as it is for everything that has a steric number of 5. And since we have 1 lone pair, you can go back and double check this, but this gives us a seesaw structure. So a seesaw molecular geometry. Let's go ahead and sketch it as well. We're often asked to do that as well. And so that'll give us an S like this, lone pair on the side, and then all the fluorines here, 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 and here. All right, and one other thing you may be asked is all the bond angles. So this bond angle will be something less than 90 degrees, and this bond angle here will be something a little bit less than 120 degrees. All right, so and that's it. That's the solution to our problem. So let's go ahead and do a couple more. Maybe one more. I think will be a good use of our time on this video. Okay, let's do this molecule, xenon tetrafluoride. Right, a weird molecule, not a very common one. But a fun one to do in terms of looking at molecular geometries. Okay, so again, step 1, we're going to draw the Lewis structure, and then from there figure out how many bonding pairs, how many lone pairs, what's the steric number, what's the electron domain geometry, what's the molecular geometry. So that's sort of our steps that we're going to go through. Okay, so xenon, being a noble gas, has 8 valence electrons, and for the fluorines we have the same thing. We have 4 atoms with 7 valence electrons each. So that gives us a total of 28 plus 8, which is 36 electrons. All right, xenon is going to be our central atom here. We need to put the 4 fluorines around, and we won't worry about the geometry yet. We just need to attach all of them. Add all of our lone pairs on the outside atoms, and then count up. So this is similar to the SF4 we just did. In this structure, there are 32 electrons. We need 4 more. And so we're going to add lone pairs on the xenon. I'll draw them as dots. So we're going to have 2 lone pairs on the xenon here. Okay, so this is going to have a different geometry than the problem we just looked at. So SF4 has the seesaw structure. Xenon tetrafluoride, we can see we have 4 bonds, 2 lone pairs. So that gives us a steric number of 6, right? Just adding those two together. And with 2 lone pairs, that means we're going to put our lone pairs on opposite sides. So the electron pair geometry here is octahedral. And our specific molecular geometry is going to be square planar. And that's because we have those two lone pairs. So what this is going to look like is xenon with 4 fluorines right in the plane of the molecule. And again, our lone pairs are pointed straight up and straight down. They're just opposite sides to each other. Now we could alternatively draw this way. This is exactly the same structure where everything's at right angles to each other. And here the lone pairs would be sort of on top and behind the page, the plane of the drawing that I have here. So this is just, these are equivalent structures. One's just flipped this way. So the one on the left is sort of oriented like this. The one on the right, you now flipped it this way. Okay, and so we're going to get a lot more practice, but this is the sort of way that we address this. So, and then final thing is, what are the bond angles? Well, all of these have an angle of 90 degrees and exactly 90 degrees. So we don't have to worry about lone pairs. Since they're on opposite sides, they have equal and opposite effects, and so they push the equal amount, so we get the ideal geometry here. All right, and so we're going to get lots more practice with stuff like this, but this concludes our beginning section on VSEPR theory, and as we move forward, we're going to look at some additional consequences of what these geometries can mean for molecules.